Performance characteristics of an induction motor, circuit model of induction motor, as we seen in the previous video. Now, the rotor current IR and the stator current IS can be found from the circuit model, where RR and XR refers to the stator windings. Once the value of IR and IS are known, the performance characteristics of the three-phase motor can be determined as follows. The stator copper loss PSU is given by 3 IS square RS, that is equation 6, and the rotor copper loss PRU is equals to 3 IR square RR, that is 7, and core loss PC equals to 3 VM square divided by RM, which equals to 3 VS square divided by RM, let it be 8. Gap power passing through the stator to the rotor through air gap is given by PG equals to 3 IR square RR by S, let it be 9. Now, developed power is given by PD equals to PG minus PRU. Then substitute these values, 3 IR square RR by S minus 3 IR square RR. 3 IR square RR by S of 1 minus S. That is the equation number 10, which we can write developed power PD equals to, this is nothing but PG of 1 minus S, let it be 11. Developed torque TD is given by developed power PD divided by omega m. That equals to PG of 1 minus S divided by omega S of 1 minus S. That equals to PG by omega S. That is big to wall. Now, the input power, that is PI, is given by 3 VS IS cos theta m, let this be 13. That PI is given by the core loss PC plus the stator copper losses PSU plus the developed power PD, where theta m is the angle between IS and VS. Then the output power P naught is given by PD minus P at no load. This is the 14th equation. Now, the efficiency theta equals to the output power divided by the input power Pi. That equals to PD minus P at no load divided by Pi, that is PC plus PSU plus PD. Sorry, this is nothing but the gap power PG. Then this is PG. Let it be 15. Now we got the equation for the efficiency. Now if that PG in the denominator is greater than PC plus PSU and PD is greater than P at no load, then the efficiency is given by PD by PG, that equals to PG 1 minus S divided by PG, that equals to 1 minus S. The value of Xm is normally large, and Rm, which is much larger, can be removed from the circuit model to simplify the calculation. Then if Xm square is greater than Rs square plus Xs square, then Vs is approximately equals to Vm. And magnetizing reactance Xm may not be moved to the stator winding. To simplify further, then we can show that and this is approximated per phase equivalent diagram. Now, the input impedance Zi of the motor becomes Zi equals to minus Xm Xs plus Xr plus J Xm Rs plus Rr by S divided by Rs plus Rr by S plus J Xm plus Xs plus Xr. The power factor angle of the motor theta m is given by pi minus tan inverse of Rs plus Rr by S divided by Xs plus Xr plus tan inverse of xm plus xs plus xr divided by rs plus rr by s. That is equation number 16. Now from this circuit, the rotor RMS current IR is given by Vs divided by Rs plus RR by S whole square plus Xs plus XR whole square under the square root. That is the equation number 17. Substituting 17 in 9, and then equation number 12 yields to TD equals to 3RR Vs square divided by S omega S of Rs plus RR by S square plus Xs plus XR whole square. Let this be equation number 18. If the motor is supplied from a fixed voltage at a constant frequency, the developed torque TD is a function of the slip, and torque speed characteristics can be determined from this equation number 18. A typical plot of torque speed characteristics of an induction motor is as shown here, where the y-axis belongs to the torque, x-axis belongs to slip as well as the speed. The operation in reverse motoring and regenerative braking is obtained by the reversal of the phase sequence of the motor terminals. The reverse speed torque characteristics are as shown with these dotted lines. There are three regions, that is first one motoring or powering, where the slip is going to lie between 1 and 0. Slip is 0 and 1. In motoring, the motor rotates in the same direction as the field, and as the slip increases, the torque also increases while the air gap flux remains constant. Once the torque reaches its maximum value, that is Tmm, at S equals to Sm, the torque decreases with the increase in the slip due to the reduction of air gap flux. Now second region, regeneration, is in between S is greater than 0 in this region. In regeneration, the speed omega m is greater than the synchronous speed omega s, with omega m and omega s being in the same direction as shown here, and the slip is negative. Therefore, RR by S is negative. This means the power is being fed back from the shaft to the rotor circuit, and the motor operates as generator. The motor returns power to the supply system. The torque speed characteristics is similar to that of the motoring, but having the negative value of the torque. As you can see, this plot is same as in the motoring, but in negative direction. The third region, plugging, which is going to lie between 1 and 2 of the slip. In reverse plugging, the speed is opposite to the direction of the field. You can see omega m is in anti-clockwise, whereas omega s in clockwise. The slip is greater than the unity, you can see here. This may happen if the sequence of the supply source is reversed while forwarding motoring, so that the direction of the field is also reversed. The developed torque, which is in the same direction as the field, opposes the motion and acts as a braking torque. Since S is greater than 1, the motor currents will be high, but the developed torque will be low. The energy due to the plugging brake must be dissipated within the motor, and this may cause excessive heating of the motor. This type of braking is not normally recommended. At the starting, the mission speed is omega m equals to 0 and S equals to 1. The static torque can be found from the equation number 18, that Ts equals to 3 RR Vs square divided by omega S of Rs plus RR whole square, as S is 1, plus Xs plus XR whole square. That is equation number 19. The slip for maximum torque, as we've seen from the figure, maximum torque occurs at Sm, can be obtained by setting d Td by Bs is equals to 0. Then the equation number 18 yields to Sm equals to plus or minus Rr divided by Rs square plus Xs plus Xr whole square holding another square root. Let it be equation number 20. Now substituting S equals to Sm in equation number 18 gives the maximum developed torque during the motoring, which is also called as pull-out torque or breakdown torque. That pull-out torque or breakdown torque Tmm is given by 3 Vs square divided by 2 omega s of Rs plus square root of Rs square plus Xs plus Xr square under the square root. This is equation number 21. Now the maximum regenerative torque can be found from the equation number 18 by letting S equals to Sm. Then Tmr, that is this torque negative, is given by 3 Vs square divided by 2 omega s minus Rs plus square root of Rs square plus Xs plus Xr whole square. Let this be equation number 22. Now if Rs is small when compared with other circuit impedances, which is usually valid approximation for motors of more than 1 kilowatt ratings, the corresponding expressions will become that Td equals to 3 Rr Vs square divided by S omega s of Rr by S plus Xs plus Xr square. Let it be equation number 23. Then Ts will become the equation number 19, that 3 Rr Vs square divided by omega s of Rr square plus Xs plus Xr whole square. Let it be equation number 24. Then Sm equation number 20 will become plus or minus Rr divided by Xs plus Xr. Let this be equation number 25. And Tmm will become minus Tmr, that equals to 3 Vs square divided by 2 omega s of Xs plus Xr. Let this be equation number 26. Now normalizing the equations 23, 24 and 26, it is going to give us Td divided by Tmm equals to 2 Rr Xs plus Xr divided by S of Rr by S whole square plus Xs plus Xr whole square, which equals to 2S Sm divided by Sm square plus S square. Let this be equation number 27. And Ts by Tmm is going to be equal to 2 Rr Xs plus Xr divided by Rr square plus Xs plus Xr square, which equals to 2 Sm divided by Sm square plus 1. Let this be 28th equation. If S is less than 1 and S square is less than Sm square, then equation number 27 can be expressed as Td divided by Tmm equals to the equation number 27 2S divided by Sm, that equals to 2 of omega s minus omega m divided by Sm omega s. Let this be 29th equation, from which omega m is given by omega s of 1 minus Sm divided by 2 Tmm multiplied by Td. Let this be equation number 30. Now, it can be noted from the equation number 29 and 30 that if the motor operates with a small slip, the developed torque is proportional to the slip and the speed decreases with the torque. The rotor current, which is 0 at the synchronous speed, increases due to the increase in Rr by S as the speed is decreased. The developed torque also increases until it becomes maximum at S equals to Sm. For S is less than Sm, the motor operates stable on the portion of the speed torque characteristics. If the rotor resistance is low, Sm is low, that is, the change of motor speed from no load to the rated torque is only a small percentage. The motor operates essentially at a constant speed When the load torque exceeds the breakdown torque, the motor stops and the overload production must immediately disconnect the source to prevent damage due to overheating. It should be noted that for S is greater than Sm, the torque decreases despite an increase in the rotor current, and the operation is unstable for most motors. The speed torque of an induction motor can be varied by one of the following methods. First one, stator voltage control. Second one, rotor voltage control. Third one, frequency control. Fourth, stator voltage and frequency control. Fifth one, stator current control. Sixth one, voltage, current and frequency control. To meet the torque speed duty cycle of the drive, the voltage, current and the frequency controls are normally used. We will see that different methods of controlling in the next video. This is regarding the performance characteristics of an induction motor. If this video is useful, please like, share and subscribe.